This one is 3.18. Here a section of scaffold which consists of a plank is laid across two supports and extending a distance A on the other side of the supports here. A mason is working at the center of the plank. He thinks that he should stack his supply of bricks on the end of the plank in order to minimize the bending moment in the plank. So this is the mason here, and these are the bricks that he is stacking, and he thinks that because of these bricks the bending moment can be minimized. So let's see if there was these bricks not there. So in that case, because there is a load here because of the weight of the mason, this beam may deflect or bend in this manner. Okay, now when you bring these bricks on the side, there will be this weight coming because of these bricks. So these ends will start going inwards in this sense, and your beam deflected shape is going to be in this manner. So clearly we can see that there is less bending happening when there are bricks stacked at the ends of it. So that means he is correct. Now in the next part, if there are equal number of bricks that are stacked at the each end of the plank, for what weight of bricks WB, the maximum bending moment in the plank is minimum. So we need to go across the length of this beam, find out the location where the bending moment is maximum, and we need to minimize that maximum value of bending moment. The weight of the mason is given as Wm. So let's idealize this beam and look at the bending moment diagram for this first. So we have this beam right here. Now on this beam we have this weight because of your bricks, weight here because of bricks, the weight here right now from the mason, and there will be these two supports, one right here and one right here. So let's mark these values. This one is WB, this one is WM, this one is WB, and these reactions are R1 and R2, and because of symmetry here, both of these values are going to same, and the value will be WB plus WM divided by 2. Now there are only point loads in this beam right here, so we can use our basket method. So in the basket method, we start walking from this side and start collecting the positive forces for your shear force diagram. Okay, so when I start from this side, I see there is a negative force WB there. So in this first segment, we are going to have minus WB as your shear force. When I reach this point, I notice there is R2 which is in the positive direction, so I'm going to add R2 to this minus WB. So minus WB plus R2 value is WB plus WM over 2. So you see that now we are going to shift to WM over 2. So now this right here is WM over 2. After that, when we reach this point here, we have WM going down, so we are going to subtract WM from here. So on this side we are going to get minus WM divided by 2, and after that again we get R1 which is going upwards, so minus WM divided by 2 plus R1 which is WB plus WM divided by 2. So this cancels out, so here again we get a positive value which is WB. So now I can connect all this. So this is how your shear force diagram is going to look for this beam. Now for the bending moment, we can look at the area under this curve in the shear force diagram. So in this part here, your area will be increasing but on the negative side, and by the time it reaches here, you will be covering a distance of A. So total area that we get from this section is going to be minus WB times A at this point. Okay, after that in this segment here, your area is increasing in the positive side. So that means your area will increase in this manner and it may reach a positive value somewhere here. And how do we calculate the total at this point? Total at this point is going to be this minus WB times A that comes from the first segment here plus what we get from this one right here. So this is going to be WM divided by 2 times the length here, and the length here is L by 2 minus A. So we can multiply this by L by 2 minus A right here. Now when we repeat it for the next step, again we are going in the negative direction here, so your area will drop. So it drops in this manner, and in this segment your area again goes to the positive direction, so you start increasing your area. So that's how you get your bending moment MBX right here. Now there are two values that are important to us, this one right here and this one right here. So when we think in terms of the maximum value of moment, the absolute value of this moment will be considered, right? So either on the positive side we take this value or the absolute value of this one right here. So this is a positive value, this one is a negative value. So if you want to have this to be a minimum, you need to compare both of these. So minus WB times A plus WM divided by 2 times L by 2 minus A, that's the maximum possible on the positive side, equals to the absolute value of this, meaning WB times A. So if I solve for the weight of bricks from here, we get WB is going to be WM divided by 4A times L by 2 minus A. So this is the weight of bricks that will minimize the maximum value of bending moment. So maximum can happen either at this point or it can happen at that point, and it will be minimum when both of these values will meet each other.